Hello, welcome to the next video of the lab one. In this lab, we are going to design a seconds counter and we are going to display on the 7-segment display. So in the previous video, we discussed the design of the clock division circuit and we generated the 1 Hertz clock from the 100 megahertz clock. Now we are going to design a counter which mod 60 counter to count the number of seconds. And then we are going to convert that binary number into the BCD number so that we can display it on the 7-segment display. Okay, so now our next task is to design digital clock module for seconds. Okay, later we'll be adding the minutes and other things, but right now we will focus it on the seconds. Okay, so this is the digital clock module. Instance name is MD. So the input to this is my 1 Hertz clock. Okay. Then it will have the reset as an input. And the third output will be the binary output of the second value. Okay. So this is the second binary. Okay. And this binary second, since it counts from 0 to 60, we need to define it as a 5-bit signal or 6-bit signal, because it's a 2 to the power 6 is you can go up to 64. Okay, so we need to define it as a second binary as a 6-bit signal. So basically, this digital clock module will accept the 1 Hertz clock. It will design a counter which counts at the increment of every 1 second using the 1 Hertz clock. And it will generate the output, which is the mod 60 counter. It will count from 0 to 59 back to 0 to 59. So it's a simple design of a mod 60 counter. Okay, so let's design this module. Add sources, design sources, create file. The input is clock 1 Hertz. You can use it here or you can add it later. You can reset, and output is the second binary, which is the output, and it's a bus of 6-bit, so it's a 5 down to 0. Okay, clock 1 Hertz and this one. So let me save it so that you can see it is inside the digital clock module. Okay, so seconds binary. Now again, it's a basically a counter. So let's define the two variable, register and next. So register 5 down to 0, second count, which is register 0, register 5 down to 0, second count, next. Don't initialize the output of the combinational circuit, it is not possible. Then we have the always at first edge of clock 1 Hertz. Okay, and here I am making the reset as a asynchronous reset. The reason you can apply your logic and find out why the reset should not be a synchronous reset. Okay, try to find out the logic for this circuit. Then if reset is equal to 1, then second out range is equal to 0, else range is equal to next. Okay, so this is my sequential circuit. Then my combinational circuit, always at start, begin, end. So what I need to do here is that I need to increment this counter by 1, but whenever it reaches the 59, I need to reset it to 0. So by default, I'll assign some value to the this way output of the combinational circuit. Now, if count edge is equal to 59, it reaches the 59 on the next clock edge. Okay, it will be equal to 0. If it is not 59, okay, then sorry, next is equal to second register is equal to +1. Okay, by now you should know that in the combinational circuit, you should always use the register output as an for any assignment. You should not use the next output. Okay, again, you should find out the reason why you should not do the second count next is equal to second count next +1. It should always be a register +1. Okay, and then my output, I'll assign it, assign second output. It should be always a flip-flop or sequential circuit output because it changes only at the positive edge of the clock and not the next, which can change anytime. Okay, so you need to be careful about this one. So this is a very simple circuit of the seconds counter. Okay, now the one thing I told you that I want to make the reset as asynchronous. Why this is important? You need to understand that this reset signal is used here also as well as here also. So when the reset is pressed 1, your clock will be stopped. What does it mean? If the clock is stopped, that means you can see that if you don't use the asynchronous reset, if the clock is stopped, you are not going to enter inside the loop. So even if the reset is equal to 1, it is not going to affect the circuit. So that's why I have made this as a asynchronous reset. So even if the clock is stopped because of the reset of the previous module, this reset will happen and my count will be resetted to 0. Okay. And these things will come to know only when you design the circuit and you don't get the desired functionality. And when you debug it, then you will come to know. Or you will, when you write the test bench appropriately, then you will know the what are the changes you need to do inside your code. So this is complete. So we got the binary output. Now the next task is to, so my task 4 is to convert my binary output into the BCD so that it can be displayed as a digits on the 7-segment display. So convert binary to binary coded decimal for display on 7-segment display for 7-segment display. Okay, and to convert the binary to the BCD, there is a well-known algorithm. If you go to the Wikipedia page and you just type the binary to BCD, you will see this double algorithm. Okay, and it tells you how to convert the binary number to the BCD. For example, this binary number is for the 243. Okay, but to display on the 7-segment, you need a separate digits 2, 4, 3 separated up. So you can see that the corresponding BCD is 2, then this is 4, and this is 3. And to convert this number, it's a very simple step. Suppose this is your 8-bit number. You need to do the 8 shift. So basically, you start with the output all the 0. You shift the number to here. Okay. Then you shift the next number. And whenever this number, any of these numbers becomes greater than 5, you basically add 3. For example, this number is 7. You basically add 3 and you get the 10. Okay. So then then you perform the shift so that this number goes here and this number becomes less than or equal to 5. So you need to repeat these things again and again. Whenever the number becomes greater than 5, you need to add the 3 to that one. And the number of shifts you need to do is equal to the size of your input number. And writing the Verilog code is very simple. So we'll write the corresponding Verilog code from the scratch. Though they have provided the Verilog code, but at the bottom, but we'll write it our own Verilog code to understand the process. Okay. So what we are going to do is that we are going to do the binary to BCD. Okay. Code. So the first is we need to provide the binary input, which to be converted into the corresponding BCD. Okay, and this binary input is this one, but we need to make sure that we only display the positive number because there is we need to display it on the BCD. So what we are going to do is that we are going to add the MSB 0 so that the if this number is always taken as a binary number. Okay, so we'll add the 1 bit of 0 so that this number is always taken as a binary. Okay, so that is the requirement of this algorithm. Then what we are going to do is that we are going, once we give the number, we will get the output. We'll get the output at the 0th digit, that is 1st digit, 10th digit, and the 100th digit. Because here you can see that our seconds can go from 0 to 60. Okay, so we usually have only ones and tens number, but for the future perspective, we'll write the code so that we can have the ones, tens, and the as well as hundreds number also. Later, you can extend the thousands number also. Okay, so let's have the output. First is the BCD at the ones place. Okay, so for now, we are going to use the second. So this is 1 second. Okay. Then because we can use this for the minutes and all those things. So that's why the code will be independent upon your input. BCD, then add the tens place. So that will be my tens second. And then I'll have the BCD and the hundreds place. So that is my second. Okay, so this is my code which takes the binary input and converts the BCD. So we assume that the binary input is around 7 bits, so it can go from the 0 to 127, and then the output will be the 3 digit. One is at the ones, then tens, and the hundreds. So these are the 3 outputs. So each output we need to define. So these outputs will be, so each digit is a 4-bit number because it can go from 0 to 9. Okay, so that's why it is a 4-bit number. So that is 1 second, then that is 10 second, and that is 100 second. Okay, so that is the 4-bit number because each digit can go from 0 to 9 in the BCD. So now we'll write the code for this one. Okay, so my input is binary input, which is I think it is the 8-bit number. So 7 down to 0. Then BCD ones. This is the output. This is my 4-bit number. BCD tens. This is again output. This is my 4-bit number. BCD hundreds. This is my output. Again, this is my 4-bit number. Click OK, and the corresponding files will be added. Okay. So here you can see that we need to first do the shift operation, and this shift operation will be the number of times is equal to number of bits in the input. So here you can see that we need to do the shift operation by 8 times, and then we need to keep a track of which those 4 bits are greater than 5. Okay, so the code is not that difficult. So we'll define the first counter for the counting the number of shift. So it's basically a for loop. So it's a shift count. Okay. And then we will need to define the internal register. So if you go to the this one, you can see that internally you need to store all these values in somewhere. So this number, it will get shifted, but you need to store all these values. So what we are going to define is that internal register, which is the total 20 bits, total 8 outputs plus 12 outputs, 444, and 8 inputs, so total 20 bits. And this I'll define it as a internal shift. Again, you can get this code online also. There are multiple sources where you will get the similar code. So then always at whenever my input changes, I need to perform this operation, begin and end. Okay, this circuit should work whenever my input is changing. Okay, so whenever the new input comes, what I need to do? I need to update this one. So this internal register, you can see that my last 12 bits, okay, it should be initialized to 0. As you can see in the algorithm, the last 12 bits are initialized to 0, and then 8 bits are the input number. So then I have the internal shift, 7 down to 0, my binary input. Okay. So first step I need to do is that I need to prepare my internal list. Then I need to do the 8 shift. So for that I'll use the for loop for my shift count is equal to 0. Shift count is less than 8. Shift count is equal to shift count plus 1. I'm going to do the end times shift. So this is begin and end. Now for every shift, I need to check whether each of those 4 digits are greater than 5. So what I'm going to do, I'm going to check each one. So internal shift, the first one, 11 down to 8. If it is greater than or equal to 5. If it is greater than or equal to 5, I'm going to add the corresponding 3 to that. So internal shift 8 to 5 is equal to 8 to 5 plus 3. Okay. The same thing I'll be doing it for the next those 4 bits. So then I have the 15 down to 12. 15 down to 12. Again, I'm going to increment it by 3, and then 19, 16, 16, I'm going to increment by 3. Okay. And the important operation is that I need to do the shift operation. So I'm going to do the internal shift is equal to internal shift by 1 bit. Okay. This will happen at the 8 number of times, and at the output, I'll get my all the 3 output. So the BCD ones, okay, is equal to internal shift of the 11 down to 8, because first 7 bits are my input data. Then BCD tens is equal to 15 down to 12, and BCD hundreds is equal to internal 12 is equal to 19 down to 16. Okay. So this is very simple code where we converted the binary number into the BCD number. Okay. So basically we do the 8 times shift, and we check every time whether those 4 digits which are the expected output of the BCD are greater than 5 or equal to 5. And if yes, when, then we increment the corresponding number by 3. Okay. So this completes our BCD to binary. Now the final step after we convert the BCD to binary is to display the corresponding binary to BCD, then display the corresponding BCD output. You can see that the ones, tens, and hundreds will be 0 for now. So we'll be displaying the ones and tens on the 7 segment. So in the next video, we are going to discuss how to display some digits on the 7 segment display which is there on the board.